Welcome to this deep dive. Today we're tackling, well, a really fascinating area of AI. How these intelligent agents figure out what to do, especially in really complex situations.
Right, where you just can't write down all the rules beforehand.
Exactly. It all revolves around this core idea of value. We've had quite a few listeners ask about value function approximations and also the thinking behind deep Q networks, DQN.
Yeah, those are definitely big topics. Powerful stuff.
So that's our mission. We're going to break these ideas down, starting right from the basics, what value even means to an AI. And then we'll build up to how systems learn smart moves without, a giant instruction book.
And we'll be leaning on Sutton Mombardo's reinforcement learning book quite a bit. It's pretty much the go-to text.
Okay, so where do we start? What's the ground floor here?
Ground floor is really reinforcement learning, or RL. Think of it like training a pet. You don't explain the physics of sitting.
Huh, no. You just give a treat when they do it right.
Precisely. RL agents learn like that. They try stuff out, take actions, and get feedback. Usually it's just a number, a reward signal.
Okay.
And the goal, the agent's whole purpose, is to figure out a strategy, which actions to take in which situations to get the most reward possible. But crucially, over the long run.
Not just the immediate treat.
Exactly. It's about maximizing the total reward collected over its entire lifetime, essentially. Think, playing chess. You want checkmate, right? Not just grabbing a quick pawn if it ruins your position later.
Right, the long game. That makes sense.
That long-term view is absolutely key.
Okay, so if it needs to think long-term, how does it judge whether it's in a good spot or if a move is smart? Just guessing.
Well, that's where value functions are critical. Instead of just looking at the immediate reward, the agent uses these functions to estimate the expected future rewards.
Okay, estimating the future. How?
It asks questions like, how good is it, really, to be in this state? Or how good is it to take this specific action right now, given where I am? It's all about the potential future payoff.
Like in that chess game again.
Perfect analogy. So you've got the state value function. Think of it as asking, overall, how good is this board position for me, assuming I play according to my current strategy? We usually call it V of S.
V of S. Got it. How good the state is.
Yep. Then there's the action value function. This one's more specific. Okay, in this position, how good is making this particular move right now and then sticking to my strategy afterwards? That's Q of S and A.
Q of S and A, the value of taking action A in state S.
Exactly. And the cool thing is, agents can learn these values just from experience. Play lots of games, see what rewards you actually get from different situations, and average them out. That's kind of the idea behind Monte Carlo methods.
Learning by doing and seeing what happens.
You got it. Now, the ultimate aim is to find the best possible value functions. The optimal value functions, V star and Q star.
Optimal meaning?
Meaning they represent the absolute maximum expected future reward you could possibly squeeze out of the environment. They basically define the perfect way to play.
The perfect strategy map.
Nicely put. And there's a mathematical way to describe this perfection called the Bellman optimality equation. It's quite elegant, really. It says the value of a state, if you're playing optimally, is equal to the reward you get from taking the very best action plus the discounted value of where you end up after that action, assuming you keep playing optimally.
It connects the best now to the best future.
Perfectly stated. It's the blueprint. But, and this is a huge but.
I sensed a but coming.
Yeah, it's the curse of dimensionality. For almost any interesting problem, chess, Go, robotics, even simple things sometimes, the number of possible states or state action pairs is just mind-bogglingly enormous.
More states than you could ever list.
Way more. Think about chess positions. It's astronomical. You could never, ever build a table in a computer to store a separate value for every single one. Not enough memory, not enough time to visit them all.
So the table idea breaks down completely for big profit.
Completely. It's just not feasible.
Okay, so what's the fix? How do we handle this curse?
The fix is a really clever idea. Function approximation. Instead of a giant table, we use something much smaller, like a mathematical formula, or, very commonly these days, a neural network.
A neural net, like the ones used in image recognition.
Exactly like those, yeah. We use this function, which has a limited set of adjustable knobs, or parameters, we call them weights, WOW, to estimate the true value function. So we have V hat approximating V, or Q approximating Q.
Hat meaning estimate.
Right. And the key insight here, the reason this works, is generalization.
Generalization.
Yeah. When you adjust one of those weights, including similar ones the agent has never actually visited,
So learning from one situation helps you understand others like it.
Precisely. That's how AI starts to see patterns and learn efficiently, even in massive state spaces. It's absolutely crucial.
Okay, that makes sense. So you have this function, this estimator. How do you make it, well, better? How do you tune those weights? Do you have a
Good question. The standard approach is using gradient descent methods. Basically, you compare the function's current estimate with some target value, like the actual reward you got, plus your estimate for the next state.
the target is like what the answer should be.
Kind of,
Yeah.
yeah. Or at least a better estimate than what you had before. Then you calculate the difference, the error, and you adjust the weights a little bit in the direction that reduces that error.
Nudging the estimate closer to the target.
Exactly. The basic update looks like new estimate gets old estimate plus some step size times the error target. Old estimate target, you're just incrementally improving.
And the step size controls how big a nudge.
Right, how fast you learn. Now, for the function itself, there are different types. Linear methods are surprisingly effective. They work by extracting features from the state.
Features. Like, is the car near the hill? Is the pond threatened?
Yeah, things like that. Or you can use techniques like tile coding. Imagine your state is continuous, like speed and position. Tile coding lays down multiple overlapping grids over that space.
Overlapping grids.
Yeah.
Like graph paper shifted around.
Sort of, yeah. Each little square or tile is a feature. If your state lands in a specific tile, that feature turns on. Since the grids overlap, one state can turn on features from several different grids. It gives you a flexible way to carve up the space and generalize.
Okay, so that's one way. What else?
And then, of course, there are artificial neural networks. They're very powerful function approximators. And the magic for adjusting their weights is an algorithm called backpropagation.
Backpropagation. Heard of that? That's how they learn.
It's the core mechanism, yes. It efficiently figures out how much each connection, each weight in the network contributed to the error, so you know how to adjust them to improve the prediction. It's fundamental to deep learning.
Okay, maybe an example would help pull this together.
Definitely. Let's talk about the mountain car task. Classic RL problem.
Right, the underpowered car in the valley.
Exactly. It's stuck between two hills. Goal is the flag on top of the right hill, but the engine's too weak to just drive straight up.
So you have to go backward first.
You got it. You have to drive back up the left hill to build momentum, then swing forward to make it up the right one. It's counterintuitive.
And the state is continuous position and velocity. So no table.
No table possible.
No.
But if you use an algorithm like SARSA, which is a temporal difference learning method, learning from prediction differences, and combine it with linear function approximation using that tile coding we mentioned.
The overlapping grids.
Yes. The agent can actually learn to solve it. It learns to generalize. It figures out that certain combinations of position and velocity, even if never seen before, require going backwards.
Wow. And you mentioned optimistic initialization sometimes helps.
Yeah, that's a neat trick. Sometimes you start the agent's initial Q value estimates really high, higher than any reward it's likely to get.
Why do that?
Because then, almost every real experience is disappointing compared to its initial hopes. This constant disappointment encourages it to try different things, to explore more, hoping to find those elusive high rewards it started off believing in. It pushes exploration.
Huh. Interesting psychology for an algorithm.
It kind of is, isn't it? So, with approximation handled, we can move to a really influential algorithm, Q-learning.
Q-learning. Okay. How's that different?
Q-learning is what we call an off-policy TD control method.
Off-policy, meaning
It means the agent can learn the optimal way to behave, finding that Q star, even if it's currently acting differently. Maybe it's acting randomly sometimes to explore.
so the learning policy is different from the acting policy.
Exactly.
Right.
This is super useful because the agent can explore broadly but still learn about the single best path.
How does it manage that?
The Q-learning update rule is the key. When it updates the Q value for taking action A in state S, it looks at the immediate reward R, and then it adds the discounted maximum possible Q value it could get from the next state, S prime.
Maximum. So it looks ahead and assumes it will take the best action next time.
Precisely. Even if, in reality, its exploration policy made it take a different, maybe worse, action from S prime. It learns based on the potential optimum. That max operation is what makes it off policy and drives it towards the optimal Q star.
Okay, that's clever. Learning the best path even while wandering around a bit.
Very clever. And now, the connection you've been waiting for.
Deep Q network.
Hey, Q networks. You take that powerful Q learning algorithm, and for your function approximator thing estimating those Q values, Q had. You use a deep multi-layer artificial neural network.
So Q learning plus neural network equal DQN, basically.
That's the core concept, yes. Q-learning provides the update rule, the learning signal, and the deep neural network provides the powerful generalization needed for huge, complex state spaces, like visual input from a game.
And this combination, it actually works well.
Oh, incredibly well. It's been behind some major breakthroughs, but the roots go back further than you might think. Look at TD Gammon.
TD Gammon, what's that?
Developed by Jerry Tesoro at IBM back in the early 90s, it was a backgammon playing program.
Backgammon. Okay, complex game. Lots of states with the dice rolls.
Exactly. Another cursive dimensionality situation. TD Gammon used a TD algorithm, specifically TD lambda, which cleverly blends short-term and long-term feedback combined with a neural network for function approximation.
Just like the DQN idea.
Very similar principles, yes. The network learned to estimate the value of board positions, technically after states, the position after its move but before the opponent's, and it learned using gradient descent and backpropagation.
How did it learn? Did experts teach it?
That's the amazing part. No experts needed, really. It learned primarily by just playing games against itself. Millions and millions of games.
Playing itself. Wow.
Generating its own data, its own experience, and from that self-play, it reached a level of play comparable to the best human grandmasters in the world at the time.
Without being explicitly programmed with human strategies.
Largely without them. It discovered strategies that sometimes surprised human experts. It was a landmark achievement, showing that these learning principles, combined with function approximation, could achieve superhuman performance in complex tasks.
That really drives home the power of this approach.
Yeah.
Handling huge state spaces.
Yep. Learning directly from raw experience, even simulated experience.
Without needing a perfect model.
Right. And crucially, generalizing what it learns. TD Gammon didn't memorize every backgammon position, it learned patterns.
It's easy to see how that blueprint leads to modern AI in games, robotics, all sorts of things.
Absolutely. It laid so much groundwork.
So quite a journey today. We went from just understanding value in RL
To seeing why simple tables fail and we need function approximation.
tackling that cursive dimensionality.
And finally, seeing how Q learning paired with neural networks like in TD Gammon and modern DQNs lets agents learn incredibly complex skills.
It really feels like we've unpacked something fundamental about how intelligence can emerge from simple rules and experience.
It does, and it leaves us with a really interesting thought, doesn't it? This whole idea of agents learning value and optimal behavior through approximation and experience.
What's the thought?
Well, just think about all the complex systems around us. Traffic flow, power grids, logistics, maybe even complex scientific discovery. If these principles let an AI master backgammon from scratch or learn to control robots, what happens when we apply them more broadly?
You mean, what new problems could we solve?
Exactly. What new capabilities could emerge if we empower systems to learn and approximate optimal behavior in all sorts of intricate real-world domains? It makes you wonder what the next TD Gammon moment might be, and in what field.
That's definitely something to chew on. The potential seems enormous.